All right, and welcome back to our series on Tellurium. This is part two. If you haven't seen part one, please go check it out. But for a quick refresher, we covered a brief history of Tellurium and key contributors from the Sorrow Lab, key functionality of the package using some code examples, two simple models of reaction networks, the steady state, and the stoichiometry matrix. In this video, we're going to expand upon these topics and learn about some advanced functionality of Tellurium and look at a more complex model. And we're also going to talk about the systems bio markup language for model reproducibility. All right, let's jump in. Okay, so we're going to go ahead and get started here by looking at this repressor network. So this can be generalized, but we'll imagine that it's a gene network. So we'll start here with our transcription, and once we produce RNA and protein, we might have a cascade of reactions such as phosphorylation, and we're going to detect that we have a high concentration of a later reactant. And this is actually going to start repressing our initial transcription V1 so that it reduces the rate of this pathway, okay? And so we're going to model this by using our simple mass action kinetics, but we're going to have an additional term here for V1 because of this repression. Okay, so it's going to look a little bit interesting here to start, but we know that it's going to be dependent on the concentration of X3, and we're going to define this extra constant here, Ki. And lastly, we're going to have this N here that allows us to specify how strong this repression is, okay? But other than that, our rates are all going to be as we would expect here with the mass action kinetics. And it's going to be helpful for us to practice encoding this information somehow, right? So in the previous video, we talked about our stoichiometry matrix N. Okay, so we'll remember here that we can define N with the species of interest as rows and then the reaction rates as columns, okay? So based on our rates of production and consumption, we can go ahead here and fill in the stoichiometry matrix, okay? And we're going to look at all of this in Tellurium and see how we can match these findings and visualize them in the code, okay? So we're going to go ahead and move to VS Code now. Okay, so I went ahead and loaded in our model here. So again, I used the te.loada function, and then I wrote out our model network exactly as we have just walked through it. And then I also specified the parameters here. So the two things I want you to notice are that I used a dollar sign with the x0, making it a constant input. So it's not going to go down. Okay, so we're going to always be feeding into this network. And I've specified n equals 2 right now. Okay, so we're going to go ahead and just initially take a look at this. And we might simulate it for 50 seconds and get a total of 500 points. So when we go ahead and plot out the results of this network, we will see here that we start with some little oscillations in the species of interest, and then they sort of flatten out here. And it looks pretty stable. It gets to the steady state at the end. Okay, so there are many methods that we can call here to understand more about our simulation. If we even type r dot, we'll see all these potential options for methods that we can call. Okay, but we're going to start with the full stoichiometry matrix because we're familiar with that. And when we run it, we'll see exactly what we previously defined. Just notice that x2 and x3 are switched there. Okay, and we can also take a look at the steady state by getting the rates of change named array, okay? And that is going to say all of our rates of change are to the -6 power, right? So they're really small, indicating that we're at the steady state here. And lastly, if we wanted to understand the stability, we can actually get the eigenvalues, okay, the named array here. And without going too much into it, if you're not familiar, when we have a negative real eigenvalue, that is indicative of a stable system, okay? And so here, we have this stability, but actually, if we go up and we change n to say something like 20, this is going to indicate now we have a really strong feedback loop. And when we run this again, we're going to see these sustained oscillations because our feedback is now so strong that it's constantly overshooting and undershooting our steady state. Okay, so our stoichiometry matrix is going to stay the same, but our rates of change now are going to be much bigger in magnitude because we're not at our steady state, so everything is still changing. And our eigenvalues now are going to become positive, indicating we have an unstable system. So throughout these tutorials, we've built our own models and often used arbitrary parameter settings to explore these different networks. But one of the crucial elements of all this is the standardization and reproducibility of Tellurium models with the SBML language. So researchers can publish their experimentally determined parameters and models onto websites like biomodels. So here I am on biomodels, and we can take a look at the model of the month, which is of metformin for diabetes treatment in mice. They have this really complex reaction network, but we can actually go directly to the model, get some more context here, then go straight to the files and find the SBML file ready for download. Okay, so I've loaded that SBML model into Tellurium and plotted it, and we can see that there's so many different compartments where they're tracking the metformin concentration in the mice. We can actually take a look at the rates of change to understand what's happening in the simulation, and we see that, for example, the liver and the muscle have really high rates of change of metformin concentration still. So we can take a look at the floating species amount, and this is the actual concentrations of metformin in all of those different parts. So we haven't really taken a look at any of those parameters, right? Because we had K1, K2, etc. But the parameters in this model are actually all of these, right? So they're putting in the body weight and the dosage of metformin, and then all those K values for the reaction constants as well. So let's imagine we're diabetes researchers and we replicate their experiments, but instead we use a different metformin dose. So we can say the metformin dose here is 3.5 instead of what they used, which I believe was 1. And if we simulate this model again, now we're going to have some different values. And if we get the rates of change, we're going to see that all of a sudden these rates are a lot different than what we observed previously. We can again get the floating species amount, and here we have different concentrations of metformin as well. Now, let's say we continue to adapt what they've built and used various different assay protocols, different metformin doses, collected all of our experimental data, and fit it to a new model. Now, after all of that, we've made a bunch of changes, and now we can validate the SBML that we've created, and then once it passes a check, we can actually get that SBML, and now we have a whole SBML file ready to be written and uploaded back to biomodels so we can collaborate with those researchers and further this research. All right. Throughout these tutorials, we've seen how you can use Tellurium to build reproducible biomodels for research in fields like gene regulation and drug metabolism. I hope you feel ready to apply your knowledge, and thanks for watching.